Hi, I am Praveen Kumar. Today, the topic is recursion. We'll look at what is recursion, why we need to go for recursion, and we'll implement a problem using both iterative approach and then followed by recursive approach. What is recursion? Recursion is a method of solving a problem where solution to the problem depends upon the solutions to smaller instances of the same problem. Simply put, recursion can also be defined as a function calling itself. Let us understand this with an example. I want to find the Fibonacci series for a given term. Fibonacci series is a mathematical series where the current term depends upon the sum of its previous two terms. For example, if I were to say index, I am representing index as 0, 1, 2, 3, 4 and so on, and Fibonacci series for that particular index, I can represent the 0th term is always 0 and the first term is always 1. These two terms are fixed, and the subsequent terms, that is from the second term onwards, the current term depends on the sum of its previous two terms. That is, for the second term it will be 0th term value, that is 0, first term value, that is 1. So 0 plus 1, this will be the value for the second term. For the third term, it will be 1 plus 2, that will be 1 plus 1, that will be 2, and for the fourth term, it will be 1 plus 2, it will be 3. Similarly, if I were to calculate for the fifth term, it will be 5, for the sixth term, it will be 8, and for the seventh term, it will be 13. Now, given a value, let us say I want to calculate the Fibonacci series for the seventh term. This is the larger problem. I can represent the larger problem as a solution to the larger problem as a solution to smaller instances of the same problem. So this can be represented as fib of 6 plus fib of 5. So the larger problem can be represented as solution to smaller instances of the same problem. Now, if I were to represent this in the form of an algorithm, so in the algorithm, I want to approach the recursive approach we would like to go for. So it will be, the algorithm will be, if I say fib of n, first in the algorithm we'll check for the base condition. So whenever we are going for a recursive approach, we should have a base condition. When the base condition is met, the function returns some value. Otherwise, the recursive function will go into an infinite loop. So we'll check for the base condition here. The base condition is if the value of n is less than 2. That is, n is when it is 0 or 1. That forms a base condition. We return the value of n. That is, we'll return either 0 or 1. Otherwise, we'll return the value of Fibonacci series, again recursively called with n minus 1 plus Fibonacci function again called with n minus 2. Let us visualize this algorithm in the form of a solution tree. So if I were to call this method Fibonacci series for the term 7. So the value of n is 7, the base condition is not met, therefore the Fibonacci series method is again called with n minus 1 and n minus 2, that is fib of 6, fib of 6 and fib of 5. So fib of 7 calls fib of 6 and fib of 5 is not called at this point in time. This is not called at this point in time, because when fib of 6 is called, again the value of fib of this method is called with the value 6, again it will call fib of 5, which internally calls fib of 4 and so on. That means the left subtree is generated first till the base condition is met. Once the base condition is met, then the function returns a value and then the right subtree for that particular node is called. So fib of 6 calls fib of 5. Fib of 5 calls fib of 4. Fib of 4 calls fib of 3, which internally calls fib of 2, and finally it calls fib of 1. At this point, when the value of n is 1, the base condition is met, therefore the value of n is returned. So this returns a value 1. And then it is removed from the call stack. Now Fibo of 2 now calls the right subtree, that is Fibo of n minus 2. So Fibo of 2 now calls Fibo of 0, that is 2 minus 2 is 0. So since this is a base case, it returns the value 0 and then it is removed from the call stack. Now this value, return value, the previous return value was 1 and the current return value was 0. These two are added and the value, the sum of these two, that is 1, is returned to its parent, that is 1 plus 0, it returns the value 1 to its parent. Now fib of 2 returns the value 1 and now fib of 3 now calls fib of 1, that is 3 minus 2. So fib of 1, we know the value, it's a base condition, it returns the value 1. So this one from the fib of 2 is added with this one, which is the return value of fib of 1, which is now 1 plus 1, 2. So fib of 3 will now will have the value as 2. And now fib of 2 and fib of 1, after the return value to its parent, removed from the call stack. They are removed from the call stack. Now fib of 4 calls fib of 2. Now if you say fib of 2 is not the base condition, so fib of 2 again calls fib of 1 and fib of 0. Now if you see, fib of 2 is computed again. Earlier we computed the value of fib of 2 here, and after it is computed and the value returned, we remove from the call stack. But at this case, again the same subproblem, that is fib of value 2 is called, again the subtree is created and the values are computed and returned. So this subproblem is being generated again and again. We are creating the subtree and calculating the value again and again. This adds an overhead on the time complexity. So this fib of 2 now returns the value 1. So 2 from the fib of 3, the value of 2 from the fib of 3 is added with the value of 1 from fib of 2. So 2 plus 1, 3 is returned to its parent and these are removed from the call stack. All the function calls are removed from the call stack. All the previous functions calls are returned from the call stack. Now fib of 5 now calls fib of 3. Now again you see fib of 3 is not the base condition, so the subtrees again will be generated and the value is computed. So we know the value of fib of 3 which we calculated, so I'll just write the value. This will compute to the value as 2. So fib of 4 returns 3, fib of 3 returns 2, these two are added and fib of 5 will have the value as 5. And fib of 4 and fib of 3 are removed from the call stack. Now fib of 6 calls fib of 4. So again the subtree is generated. Since 4 is fib of 4 is not the base condition, so the subtrees are generated and the value are computed. But since we already know the value of fib of 4 is 3, so we will return the value 3 here. So this 5 and this 3 are added. Now fib of 6 will give us the value as 8. And now before, this is called the fib of 5 and fib of 4, they return the value and they are removed from the call stack. And now fib of 7 calls the fib of 5. And again fib of 5, that is the right subtree is generated and all the values are computed. right? So I will not be showing it here, since we already know the fib of value 5 returns the value 5. So I will write the value 5. But basically the subtrees are generated and the values are computed. So this 5 and this 8 are added and then return to its parent. So fib of 7 now returns the value as 13. And now let us look at the time and space complexity of this approach. Now there are different levels. So we have level 0, we have level 1 and so on, level 2 and so on till level n. So there are different levels. So if you see the recursive tree, the levels are from 0 to n. And at each level, if you see, each method calls internally two methods, that is fib of n calls fib of n minus 1 and fib of n minus 2. So at the 0th level, the number of function calls is 2 power 0, that is 1. At first level, the number of function calls is 2 power 1, that is 2. At second level, the number of function call is 2 power 2, which is 4. At third level, the number of function calls is 2 power 3, that is 8, and so on. At the last level, it will be 2 power n function calls. So the time complexity for this approach will be of the order 2 power n. This is an exponential time complexity and has to be optimized to a polynomial time complexity. When we look at the space complexity, we have seen that the function, when fib of 7 was called, it called fib of 6, fib of 5, fib of 3, 2 and so on. So when we look at this is the call stack, let us say this is the call stack. We have the call stack. So fib of 7 when it calls fib of 6, so fib of 7 is pushed into the call stack. Fib of 6 when it is called, it is pushed into the call stack. Similarly, fib of 5 pushed into call stack calls fib of 4. Fib of 4 is pushed into call stack calls fib of 3. So this keeps calling till the base condition is met. So these two form the base condition. So once the base condition is formed, the values of this, that is the value of 1 and 0, it is returned based on the base condition. These two are return a value and then they are removed from the call stack, that is popped out from the call stack. And when f of 2 returns, right, this is also removed from the call stack, and f of 3 here, right, f of 3 here calls f of 1. So again f of 1 is pushed into call stack. So the functions are pushed into call stack and popped out from the call stack, but the maximum number of functions in this call stack will never exceed the value n. And in the implementation of this method, we are not storing any extra, we are not allocating any extra space for any extra storage. The only value that we are storing is the parameter that is passed to that method. Therefore, the space complexity of this approach will be big O of n. Why do we need to go for recursion? Recursion is a powerful problem-solving strategy. It is a way of thinking about problems which leads to simple and elegant solution. Recursion adds clarity and reduces the time needed to write and debug the code. Let us look at the implementation of Fibonacci series for a given term. First, we'll look at the iterative approach and then followed by the recursive approach. Here, I have written a template method called as Fibo, which takes a parameter n, and this method calculates the Fibonacci series for the nth term and returns that value. I am calling this method 3 times with 3 different values. First time I am calling with the value 5 and the expected result is mentioned in the comments. So fib of 5 gives the value expected result 5, and fib of 7 will give the expected result 13, and fib of 48 gives an expected result which is a very large value which is highlighted here. So let us go ahead and implement the iterative approach. So first we'll check for the base condition. That is, if the value of n is 0 or 1, we return the value of 0 or 1. So the base condition check is if n is less than 2. Here we return the value of n. Otherwise, we iteratively compute the given term with the sum of its previous two terms. So here we'll use two variables to hold the previous value and the current value, and we iterate using a loop from the I value starting from 2, because 0th first term is already taken care by the base condition. So here we'll say int I equals to 2, that is we are starting from 2, and I is less than or equal to n, that is we want for the nth term, and we increment the value of I. So here we'll declare a temporary variable called say new term, and we assign the value with previous plus current, and now we make the previous value assigned with the value of the current, and the current value we put the value of the new term. And once we iterate through all these terms and add the new term with the previous and current term, we return the value of the current term. So this is an implementation of the Fibonacci series for a given term using iterative approach. Let us run the program and check the result. So we have got the result almost instantaneously, and the values are exactly matching with what the expected values are. So now we will go ahead and implement this method using using the recursive approach. So I will comment previous approach. I will just copy the function signature, so that now I will implement using the recursive approach. Okay, so this will be recursive approach. So in the recursive approach, first we'll check for the base condition. That is, if the value of n is less than 2, we return the value of n. Otherwise, we return the method fibo of n minus 1 plus fibo of n minus 2. That is, recursively we are calling now with n minus 1 plus fibo of n minus 2. So let us run the program and check our implementation. Now you see the fibo of 5 and fibo of 7, the expected values have come almost instantaneously, whereas for the value fib of 48, it has not yet computed. It is taking a while. Now it has come. The reason being that when we give the Fibonacci series function with a larger value, it creates the subtree again and again. Means when a subproblem is already solved, it is removed from the call stack, but again when the same subproblem is called, again the tree is generated for that particular subproblem and the value is computed. So the subproblems are computed again and again multiple times, and this adds an overhead on the time complexity. So this time complexity from a exponential time complexity has to be reduced to a polynomial time complexity. This can be done using dynamic programming. When we compare the recursive approach with that of the iterative approach which I'm highlighting. The recursive approach is simple and elegant compared to the iterative approach. So it is easy to write and debug code when we use a recursive approach. So a problem can be represented in a more elegant and simple form compared to the iterative approach. What are the issues with recursion? Recursion is usually slower due to the overhead of maintaining a stack. It usually uses more memory for the stack. Recursion can only be used when a problem can be represented as a solution to its sub-problems.